Hello class, I hope you're having a wonderful day. Today I would like to take a look at a projectile motion problem. So I'm going to read the problem, underline some important information. I've drawn a diagram and we're going to list a column of knowns and unknowns to help us solve the problem. So let's go ahead and get started. An arrow is shot at 30 degrees above the horizontal. Its velocity is 49 meters per second, and it hits the target. So there's two parts to this problem. Part A, what is the maximum height the arrow will attain? And that's identified by Y max. And so right here, we have Y max, so capital Y, subscript max. And then in part B, it wants to know the target is at a height from which the arrow was shot. How far away is the target? So in projectile motion, the horizontal distance is known as range, identified by capital R. So right here, we have range, okay? Now, some of the important information, it's 30 degrees above the horizontal, so angle theta, 30 degrees, and the initial velocity is 49 meters per second, so V sub I is 49 meters per second, okay? Now, the first thing we need to do is break this vector, the 49 meters per second velocity vector, into its x and y components. So we're going to use vector resolution here. So we have an x velocity and a y velocity. If I drew my velocity vector here, so initial velocity, 49 meters per second, and we have an x component, so initial velocity in the x direction, and we have a y component to this velocity, initial velocity in the y direction, okay? So when we're using vector resolution here, the x component, here's our angle theta, which is 30 degrees. So the initial velocity in the x direction is equal to our initial velocity times cosine of the angle theta. So we have 49 meters per second times cosine of 30 degrees. So go ahead and get your calculator. 49 cosine 30 degrees. Make sure your calculator is in degree mode. So our velocity, initial velocity in the x direction is 42.43 meters per second. And I'm just going to go ahead and label the diagram that I've drawn here. So 42.43 meters per second. Now the initial velocity in the x direction, the y direction, we have initial velocity times sine of the angle theta. So our initial velocity vector is 49 meters per second times sine of 30 degrees, and we know that sine of 30 degrees is 1/2, so 1/2 times 49 meters per second is 24.5 meters per second. So I'm going to go ahead and label the diagram that I've drawn here, 24.5 meters per second, okay? So what we want to do, we're on part A, calculate the maximum height the arrow will attain, okay? So what we need to do is our initial velocity, if I'm going to draw some more on here, our initial velocity in the y direction, we calculated to be 24.5 meters per second. At y max, so the velocity, I'll say this is my final velocity in the y direction, and we're just looking at half of the problem first. This is equal to 0 meters per second. So what we're going to have to do is calculate the time that it takes for the arrow to leave the bow and get to y max. we're going to use the base equation. The acceleration of an object is equal to the change in the object's velocity divided by the time period of that change. So this is equal to final velocity in the y direction minus the initial velocity in the y direction divided by delta t. Now this is what we're after right here, and I want to add a subscript to help us keep all of the variables straight. The time interval to maximum height. So I'm going to use a subscript of mh. What we want to do is isolate the time to maximum height by multiplying by both sides of the equal sign, and then we're going to divide by acceleration. But this acceleration that the arrow experiences in the y direction is the acceleration due to gravity. So I have delta t sub mh, so the time for the arrow to reach maximum height is equal to the final velocity in the y direction minus the initial velocity in the y direction divided by the acceleration due to gravity. Okay, so we know that the initial velocity in the y direction is 0. So I have 0 meters per second minus our initial velocity in the y direction. You have already calculated 24.5 meters per second. And then in my denominator, I have the acceleration due to gravity, which is a negative 9.8 meters per second squared. So 24.5 divided by 9.8, we're going to get 2.5 seconds. So the time to maximum height, 2.5 seconds. Now I'm going to put a dotted box around this because we are going to need this calculated value, okay? So to calculate y max, we're going to use the base equation d sub f. So the final displacement of the object is equal to the initial displacement of the object plus the initial velocity multiplied by the time interval plus 1/2 times acceleration times delta t squared, okay? Now I'm going to take this equation and apply it to what we're doing, so motion in 2 dimensions, specifically projectile motion. And this y max, this is the final displacement in the y direction. So I have y max is equal to the initial displacement in the y direction plus the initial velocity in the y direction multiplied by delta t to maximum height, so the time interval to maximum height, which we've calculated, plus 1/2 multiplied by the acceleration, and in the y direction the acceleration of the arrow is the acceleration due to gravity, multiplied by delta t to maximum height squared, okay? So I'm going to copy this information over here. So delta t to maximum height is equal to 2.5 seconds. Okay, I need the room here. So y max. Now the initial displacement in the y direction is 0. So that guy goes to 0. We don't need to mess with it anymore. So this is going to equal the initial velocity in the y direction, which you guys already have, 24.5 meters per second, multiplied by the time interval to maximum height, 2.5 seconds, plus 1/2 times a negative 9.8 meters per second squared, multiplied by time interval to maximum height squared. So once again, 2.5 seconds squared. Make sure you square this value, okay? So let's take the product of these two values, 24.5 times 2.5. This is going to be 61.25. And if you notice here, our units of seconds are going to cancel. So meters per second times seconds, or we can write this as seconds over 1. So our seconds cancel, leaving us with units of meters, plus, now, according to the order of operations right here, we have to take care of our exponent first. So 2.5 seconds squared is going to give me 6.25 seconds squared times negative 9.8, and then divided by 2. And this is going to give me a negative 30.625 meters, okay? So 61.25 meters plus a negative 30.625. So 61.25 minus, that's going to give me 30.625. Okay, so Y max is equal to 30.625 meters. So that is the answer for part A. Okay, now let's take a look at part B. Part B wants to know how far away the target is. And right here we have the range, okay? So our base equation for range is, and this is the total horizontal distance when we're talking about projectile motion, range is equal to the velocity of the object in the x direction multiplied by the total time that the object is in the air, okay? Now, you've already calculated the velocity in the x direction right here, 42.43 meters per second, but we don't have time total yet. The time interval that we calculated was to y max, and here we have delta t sub mh, and this is identifying the time interval to maximum height at 2.5 seconds. So this delta t total is equal to 2 times the time interval to maximum height. Well, time interval to maximum height is 2.5 seconds times 2. Our total time is equal to 5 seconds. So 5 seconds. All right, so our range, velocity in the x direction, we use vector resolution here to calculate the x component of our velocity at 42.43 meters per second. We're going to multiply this by a time of 5 seconds. So let's get our calculator here. 42.43 times 5. I have 212.15. And let's take a look at our units here. I have meters per second times seconds, which algebraically can also be written seconds over 1. So that means our seconds is going to cancel, leaving us with units of meters. So our range is 212.15 meters. And that is the answer for part B. So I hope this video has helped you. If you have any questions, please give me a call or send me an email. I will be more than happy to help you out. I hope you have a wonderful day.